Welcome to the strange world of quantum mechanics. Get ready to have your mind blown. Imagine a world where objects can be in two places at once, where particles communicate instantly across vast distances. This isn't science fiction, it's the mind-boggling truth about the universe at its smallest level. We'll explore the mysteries of superposition, entanglement, and the famous double-slit experiment. By the end, you'll see the universe with new eyes. Prepare to question everything you thought you knew about reality. For centuries, physicists believed they had a good grasp of the universe. Newton's laws of motion explained the world around us. Then came the early 20th century. Scientists like Max Planck and Albert Einstein made groundbreaking discoveries. The universe at its core wasn't deterministic and predictable. Instead, it was governed by probabilities and uncertainties. This new theory, quantum mechanics, proposed a radical new understanding of reality. Join us as we unlock the secrets of quantum mechanics. The birth of quantum mechanics was a seismic shift in science. It all started with a seemingly simple problem: understanding how light interacts with matter. Classical physics failed miserably. Enter Max Planck. In 1900, he proposed a radical idea. Energy, like matter, wasn't continuous. It came in discrete packets, or quanta. Soon, Albert Einstein joined the revolution, using Planck's quantum hypothesis to explain the photoelectric effect. Einstein showed that light itself was quantized into particles called photons. The very nature of light was revolutionized. As scientists delved deeper into the quantum realm, they encountered a bizarre cast of characters. The atom, once thought to be the fundamental building block of matter, was revealed to be a miniature solar system. Orbiting this nucleus was a cloud of elusive particles, electrons. But unlike planets, electrons didn't follow well-defined paths. Instead, they existed in a haze of probability, their location and momentum impossible to pinpoint with certainty. This inherent uncertainty wasn't a limitation of our instruments, but a fundamental property of the quantum world. Subatomic particles exhibited a bizarre dual nature, behaving like both particles and waves. The quantum world was a vibrant and chaotic dance of particles and forces. One of the most profound concepts to emerge from quantum mechanics was Heisenberg's uncertainty principle. Formulated by Werner Heisenberg in 1927, this principle stated that certain pairs of physical properties, like position and momentum, could not both be known with arbitrary precision. The more precisely we knew one, the less we could know about the other. This wasn't simply a matter of technological limitations, it was a fundamental limit imposed by nature itself. The very act of measuring one property inevitably affected the other in an unpredictable way. The uncertainty principle had profound implications for our understanding of the universe. It meant that the future was not preordained. Instead, it was a realm of possibilities governed by probabilities rather than certainties. Imagine walking into a cafe, ready to order your favorite drink. You're thirsty, so you ask for a superposition. The barista says, "One superposition coming right up." That's a blend of all possible drinks, existing simultaneously. In the quantum world, particles like electrons don't just exist in one state at a time. They can be in a superposition, a mixture of multiple states, all at once. Think of it like flipping a coin. Before it lands, it's both heads and tails simultaneously. It's only when we observe it, when it lands, that it collapses into a definite state, heads or tails. Until then, it's a blurry cloud of possibilities. Perhaps the most famous illustration of superposition is the thought experiment known as Schrödinger's cat. Proposed by Erwin Schrödinger in 1935, it highlights the paradoxical nature of quantum mechanics when applied to macroscopic objects. Imagine a cat sealed inside a box with a device that has a 50% chance of releasing a lethal poison. Until we open the box, the cat is in a superposition of states, both alive and dead. It's meant to illustrate the absurdity of applying quantum superposition to everyday objects. So, why don't we see macroscopic objects like cats in superpositions? The answer lies in a phenomenon known as decoherence. Decoherence is the process by which quantum systems lose their coherence, their ability to maintain superpositions. due to interactions with their environment. Think of it like dropping a droplet of ink into a glass of water. Initially, the ink maintains its shape, but as it interacts with the water molecules, it spreads out and eventually becomes indistinguishable from the surrounding water. Similarly, a quantum system is constantly interacting with its environment, air molecules, photons, even cosmic background radiation. These interactions act like tiny measurements, constantly nudging the system towards a definite classical state. One of the most mind-boggling consequences of quantum mechanics is the phenomenon of quantum tunneling. Imagine throwing a tennis ball at a wall. In the classical world, the ball would bounce back. But in the quantum world, there's a chance that the ball could tunnel right through the wall. How is this possible? It all goes back to the wave-like nature of quantum objects. According to quantum mechanics, particles don't have definite positions. Instead, they're described by wave functions which represent the probability of finding the particle at a particular location. When a quantum particle encounters a barrier, its wave function doesn't simply stop at the barrier's edge. Instead, it decays exponentially inside the barrier, meaning there's a non-zero probability of finding the particle on the other side. Buckle up, because we're about to delve into one of the most mind-bending concepts in quantum mechanics entanglement. Imagine two particles, separated by vast distances, perhaps even light years. Now imagine that these particles are linked in such a way that measuring the state of one instantly determines the state of the other, no matter how far apart they are. This isn't science fiction, it's entanglement, a phenomenon so bizarre that even Einstein called it spooky action at a distance. In the quantum world, entanglement arises when two particles interact in a way that their fates become intertwined. From that moment on, their destinies are linked, no matter how far apart they may travel. Measuring one particle instantly collapses the wave function of both, forcing them into a definite state. To understand entanglement, it's helpful to think of these entangled particles as partners in a cosmic dance. Imagine two dancers, perfectly synchronized, their movements mirroring each other with uncanny precision. Even when separated by the width of the dance floor, their connection remains unbroken. Similarly, entangled particles are linked by a shared quantum state. The key is that their properties are correlated, meaning that knowing the state of one particle instantly reveals the state of the other. It's important to note that entanglement doesn't allow for faster-than-light communication. While measuring one particle instantly influences the state of the other, we can't use this connection to send information faster than the speed of light. Einstein, despite his groundbreaking contributions to quantum theory, remained deeply skeptical of entanglement. He famously referred to it as spooky action at a distance because it seemed to contradict his own theory of relativity, which stated that nothing could travel faster than light. Einstein believed that the universe was governed by the principle of locality, meaning that objects could only be influenced by their immediate surroundings. Entanglement, with its instantaneous action at a distance, seemed to violate this principle. He proposed that there must be some hidden variables, some unknown factors that we couldn't yet detect, that were responsible for the observed correlations between entangled particles. However, experiments conducted decades later would prove Einstein wrong. These experiments, most notably those by Alain Aspect in the 1980s, definitively demonstrated that the correlations predicted by quantum mechanics were real and that there were no hidden variables at play. The implications of entanglement extend far beyond the realm of theoretical physics. This bizarre quantum phenomenon has the potential to revolutionize fields like computing, communication, and cryptography. Quantum computers, for instance, leverage the power of entanglement to perform calculations that are impossible for even the most powerful classical computers. By entangling qubits, the quantum equivalent of bits, these computers can explore multiple possibilities simultaneously, exponentially increasing their computational power. Quantum communication networks exploit entanglement to transmit information with unparalleled security. Entanglement also holds the key to unlocking new frontiers in fundamental physics. As we delve deeper into this mysterious phenomenon, we can expect even more mind-boggling discoveries that will reshape our understanding of the universe and our place within it. Get ready for the grand finale of our quantum journey, the double-slit experiment. This seemingly simple experiment, first performed in the early 1800s, holds the key to unlocking the deepest mysteries of quantum mechanics. Imagine shining a beam of light at a barrier with two narrow slits. Common sense suggests two bright bands of light, one behind each slit. Instead, we see an interference pattern, a series of alternating bright and dark bands. It's as if the light waves are interfering with themselves. Now let's fire individual photons one at a time. If we fire these photons one by one, logic dictates they should pass through one slit or the other, creating two distinct bands on the screen. After all, a single particle can't be in two places at once, right? Wrong! As we continue firing photons, something remarkable happens. An interference pattern emerges on the screen. Even though each photon travels alone, as if it should only go through one slit, it somehow knows about both slits and interferes with itself. This is the mind-blowing essence of wave-particle duality. Quantum objects like photons, electrons, and even atoms can exhibit both wave-like and particle-like behavior, depending on how we choose to observe them. But how can a single particle pass through both slits simultaneously? The answer lies in the heart of quantum mechanics. Particles don't have definite paths. Instead, they exist as probabilities, spread out in space as waves. Section 3. The Observer Effect. Reality's Fickle Dance. Now let's crank up the weirdness factor. What happens if we try to outsmart the quantum world and observe which slit each photon goes through? We set up a detector near one of the slits, ready to catch the photon red-handed. Here's the shocking part. As soon as we start observing which slit the photons go through, the interference pattern disappears. The photons, as if sensing our prying eyes, suddenly decide to behave like well-mannered particles, passing through one slit or the other. This is the notorious observer effect, one of the most debated aspects of quantum mechanics. It suggests that the very act of observation, of measuring a quantum system, forces it to choose a definite state. The implications are profound. Does this mean our consciousness influences reality? Or is it simply the interaction with the measuring apparatus that disrupts the quantum superposition? The debate rages on. Section 4. Interpretations and Implications, Navigating the Quantum Maze. The double-slit experiment, with its mind-bending results, has spawned numerous interpretations of quantum mechanics. Each interpretation offers a different perspective on the nature of reality, the role of the observer, and the meaning of quantum weirdness. The Copenhagen interpretation, the most widely accepted view, suggests that we can only talk about probabilities of outcomes, not definite realities, until a measurement is made. The many worlds interpretation, more radical, proposes that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome. The debate over the true nature of quantum mechanics continues to this day. But one thing is clear: the double-slit experiment has revealed a universe far stranger and more mysterious than we ever imagined. It's a universe where particles can be in two places at once, where the act of observation influences reality, and where the very fabric of space and time is woven from the threads of quantum entanglement. The journey into the quantum realm is just beginning, and the mysteries it holds are waiting to be unraveled. Section 1. The Quantum Legacy, a new era of understanding. Our journey into the quantum realm has taken us far from the familiar world of classical physics. We've encountered particles that exist in multiple states at once, spooky action at a distance, and experiments that challenge reality. It's a world where intuition often fails, and the only guide is the language of mathematics. Quantum mechanics has revolutionized our understanding of the universe. It's the foundation for countless technologies, from lasers and transistors to medical imaging and nuclear energy. It's also reshaped our view of the cosmos, revealing a universe far more interconnected and mysterious. The Unseen Universe, a tapestry of wonder. Quantum mechanics unveils a universe more profound and mysterious than we imagined. The infinitely small and the unimaginably vast are intimately connected. Observation can influence events, blurring the line between observer and observed. The same quantum laws shape stars, galaxies, and the fabric of space and time. It's a profound realization of our interconnectedness with the universe. Behind the beauty of the stars lies a hidden world of quantum wonders.